That's good. That's good. There we go. Found the right combination. Okay, I'm going to go ahead and start, even though people may filter in. We're very lucky to have Amir Leshem to visit us today and give us an ISL seminar, even though it's towards the end of the quarter. And he's going to be talking about a topic many people in my group anyway work on, which is cognitive radio and spectrum, finding spectrum within the white spaces of limited interference. And a little bit about his background. He got his PhD in math from the Hebrew University in Jerusalem. And I won't say the date because then I will date you. He's currently a professor at the Faculty of Engineering in Bar-Ilan University, where Yair Noam is going very soon after he finishes up with my group. And he has a very, very broad range of interests, primarily signal processing applied to wireless communication, so including multi-channel wireless and wireline, game theory applications to cognitive radio, adaptive spectrum management, array and statistical signal processing, sensor arrays, wireless communication generally speaking, let's see, radio, astronomical imaging, and brain research. Is there anything we don't do in one country? And set theory, logic, and foundations of mathematics. So if you're interested in anything in engineering or math, it sounds like you could talk to Amir and he would know the answer. So anyway, thanks very much for coming, and we look forward to it.
He was also my PhD advisor.
His biggest one. Anyway. Okay.
Of course, yeah. So, okay, thank you, Andrea, and I'm happy to give this talk. I will talk about distributed spectrum optimization, basically spectrum assignment in the open spectrum access using stable merge theorems and distributed auctions. So I'll show two different approaches to distributed computation, and the idea is to use the protocol in the multi-access channel to do computation, and basically multi-access channel can do for us more than just some signals. They can actually sort signals and do all kinds of other things, like solving optimization problems. So this is based on several works together with Yoav Yaffe, and which was our postdoc, and Efi Zahavi, and several other works with these students of Shrina Postek, which consists the second part of this talk. So what is the stable matching, and why is it relevant to spectrum location? So we are going to find, we are interested in finding a simple way to allocate spectrum to users. And we will show that actually the stable merge theorem provides a good way to do that, which we can do using what we call multi-channel opportunistic carrier sensing, which is a simple generalization of multi-channel carrier sensing or single-channel carrier sensing. So what is the problem? So basically interference is everywhere, and channel allocation currently in Wi-Fi is really bad. This is an example from my living room 4 years ago. So you can see that most of these modems are actually, most of these networks operate on channel 11. So basically, this is a very poor way to allocate it. You just assign a fixed channel in each manufacturer, and then usually people don't open the box, the configuration, and they just leave with channel 11, and they just share this channel. So this is a very bad way to do channel allocation. Nowadays, I think they randomize. This is also pretty bad in terms of spatial diversity, but okay, it's more sensible than having channel 11. It's almost chapter 11. Okay, so I will assume, so what I want to achieve is basically to look at the simple toy problem. We have n users accessing n channels, and each channel is frequency selective, so each user has different quality on each channel. And we want to allocate these channels. So this is the simple problem. It's basically an assignment problem. And we have several assumptions related to the cognitive radio. They are not always the standard one. So we assume that each user transmits on a single channel. This is common to cognitive radio system. The other assumptions are that each user is aware of network activity on all channels. So this is something that some cognitive radio researchers do not assume. They assume limited sensing. But well, the claim here is that basically having wideband sensing makes sense. It really significantly improves the performance of the network. And sensing really requires spectrum estimation. It doesn't require decoding, so it can be done with very low resolution. So it can be done by even single bit A2Ds, if you like. And we see that each user knows all his sub-channel qualities. This requires some training or some underlay signaling, wideband signaling to do channel estimation. That can be done in practice. And then the last assumption is a bit hard, but we will be able to do it, I believe, in hardware, probably even now it can be done. That each user can decide using the contention period of the carrier sensing on which channel to transmit. So basically, we have a fast channel selection mechanism which can do this during the multi-channel carrier sensing. This does not exist in current hardware. This is something that we can imagine can be done. I think a reasonable engineer can do that, hopefully. So now let's go a bit to the math. Once we agreed on the engineering assumptions. So we assume that the number of users equal the number of channels. This is not mandatory, but this makes our life simpler in terms of formulating the problem. We assume block fading. So we assume block fading, so channel qualities remain fixed over time. Or alternatively, you can think that basically all the decisions are made based on channel statistics rather than on instantaneous channel. And these are much more stable, and they can hold for a pretty long time. So for every I and J, Uij is the utility of user I transmitting on channel J. Think about it, the rate that user I can achieve on channel J when you orthogonalize the user. So we are looking at orthogonal solution. Basically, we want to allocate one channel to each user. And the question is how to do it without explicit exchange of messages between the users. So what is a matching? A matching is a one-to-one function, P from end to end, and the total utility of matching is just the sum of the utilities of I on the channel Pi which it receives. And the matching is optimal if U of P is maximal. So that this is easy. Finding the optimal matching initially might seem very complicated. We have n factorial many permutations. Actually, this is not. This is an assignment problem, so it can be solved using the Hungarian problem, which I'm going to talk about later, in n to the third many operations. But I'm going to use something else called the stable matching. So actually this year, Shapley and Brock won the Nobel Prize for Economics for development of the stable marriage theorem. And actually...
we don't need to know that.
What?
That's the most important theorem ever, right? Stable marriage.
Right. So this is, I'm going to show how to achieve it. So this is very important, especially here in California. So, but I want to notice something else. So the people that proved the stable marriage theorem are basically Shapley and Gale. But Gale died several years ago, so the Nobel Committee tried to find a game theorist that resembles him best. So obviously this is a good matching. So that's the. This was after we have done it. We didn't follow the hype. We just were a bit ahead of that. So what is the stable marriage? So the general problem is this: we have a group of like 3 men and 3 women. Each one ranks the other sex according to some preference, and this preference is arbitrary. Oops, sorry. So for example, the first man prefers A over B and B over C. The first woman prefers most man number 2, and then number 1, and then number 3. So what is a stable matching? A stable matching is a matching where no... So a stable matching is a matching where whenever we have two, like a man and a woman, or a user and a channel for that purpose, where that are not matched to each other, then either I prefers, it cannot be that both I prefers J and J prefers I over the spouses. So that means that the marriage is stable because whenever we try to match two people that are matched to other people, one of them will prefer his spouse over the other. So this is stable. Obviously, nothing will change in this there are good reasons why this doesn't hold in reality, but that's beyond the scope of this talk.
For humankind to understand.
Yeah. So let's see how can we achieve this stable marriage. So what happens is that in reality, each woman stays at home, and then in the first day, each man looks at his table and goes to the door of the woman that he prefers. So for example, both man number 1 and number 3 goes to the door of woman A, and number 2 goes to woman B, because that's his preference. Now, each woman looks out at the door and sees whether there's somebody waiting to get in. And then she chooses the one that is better. So woman A tells man number 1, you can come and sleep here, and number 3 sleeps in the woods. Actually, I've been told that number 1 should sleep on the doorstep, waiting until the process ends, till the marriage. But that was in Bar Ilan, which is a bit religious university. So then number 3 sleeps in the wood, and this is so inconvenient. So the next day he looks at his list and said, well, I cannot get A, obviously, so I would go to woman B. And he goes here to the door, and then at that day still, woman B says, well, I prefer 2 over 3. So she says, so 2 remains there, and 3 still sleeps in the wood, and then he goes in the last day to woman C, and this is a stable matching. So basically this is an algorithmic proof of the theorem. This always works. This should always stabilize. Why? Because every woman always improves her the quality of her men in this process. So each woman can improve at most n many times. There are n women, so after n squared many times, the process stabilizes. So this is basically the proof of the theorem. It can be shown that sometimes if the man stays at home and the women go out, basically we might get another stable matching. And actually, it's more interesting. There is a lattice structure of all stable matchings, and actually average number for random preferences is O of n log n many stable matchings. It is interesting that when women stays at home, what they get is, actually they improve each time, but they get the worst spouse that they can get in any of the stable matchings. So this is not actually, so it seems that women actually gain, but basically it's not so good, but that's, okay. So, but what happens about our channel location problem? Do we have n log n many stable matchings? So the answer is no. We actually have a unique stable matching. And how is that done? Basically, we have a matrix. We don't have arbitrary preferences. For every user and every channel, we have a number, and we can compare all the numbers. So basically, if we look at the matrix, there are I0 and J0, so that UI0, J0 is the maximum. I assume that all of UI, J are different, otherwise we can do random dithering to resolve these. So there is a maximal element, so obviously I0 must match to J0, so we have to remove row I0 and column J0 from the game because they are matched, and then we can continue inductively in the matrix. So we end up basically with a greedy algorithm that finds the only stable matching that exists. So this was an interesting observation, but we couldn't do much with it, so it was waiting like for a year until my postdoc actually noticed that, okay, since this is a greedy algorithm, basically we always get at least half of the optimal utility. So that's already interesting, right? So we can assure certain quality, although in wireless communication, losing half the capacity is really bad. But at least we get something. And the proof is very easy because... well, we haven't talked about pricing. So. So the proof also is easy. Basically, the largest element in the matrix is in the unique stable matching. It is larger than the first 2 elements because there must be 2 elements in the first row and the second row. It's the largest in the matrix, so it's definitely larger than the largest 2. Then, when we remove the row and column, the next one is larger than the third and the fourth. So altogether, we get that the utility of the stable is less or equal to 2 times. The 2 times the utility of the stable is greater or equal to the utility of any matching, especially the optimal one. So this is easy. This actually can be generalized to hypergraphs. Later we learned out that this was actually a well-known result, but that's not a good reason to go with half the capacity. So, but I'll show you first how this goes, and then we'll continue with the implementation, and then I'll convince you that actually maybe it's much better than 50%. It's interesting to know that for any n, you can find actually channels where the stable is half plus epsilon from the optimal. So there's no hope to improve the theorem, the half theorem. It is not in general. But what we will look later is at random channels, and then the situation is much better, basically. So how does it go? So this is an example of the Gain-Shapley algorithm. Basically, each user chooses the best channel. So user 1 chooses channel 4, and also user 2. They have a collision. So basically, user 2, which has lower utility, somehow they have to figure that out, and I'll show you later how to figure that out. He has to go to another channel. User 3 and 4 will not here. And user 5 is less than. So user 5 is less than, also chooses channel 2 is less than user 3, so he has to move, and also user 2 has to move from this channel. So then, what happens? At the second instance, they migrate. So user 2 moves to channel 1, which is the second best. And also, user 5 moves to channel 1, and actually he wins, he should get channel 1 according to the Gain-Shapley. So,
what's the convergence time?
So this is n squared.
Okay.
But I will show you that we can do it in O of 1.
Okay.
So that's, I remember that Swami once told me, well, you cannot expect better than O of n. Mm-hmm. So I will show you how to do it in a single CSMA contention period. So that's basically a nice trick. So then again, the others move, and then I should skip this, it's not that interesting. Eventually we get a rotation. This stabilizes actually here in 4 steps. And this is the final one. And the rate is not optimal. It's 293 compared to 309. So we cannot hope to get optimal stable matching. But we can ask ourselves, what happens in the random case? Suppose that the channels are IID rarely fading. So in that case, we might have hope, because for many reasons, actually, we can prove, not for the stable, but for several suboptimals. I'll show you the graph. So this is the optimal allocation. This is a simple upper bound that assumes that each user, in this case, in IID rarely fading, each user gets less than the best of n random channels. So the best of n random channels is order statistics of n Gaussian channels, and then we can get n times the highest order statistics of n random IID variables. This is an upper bound. This is a trigger upper bound. For the lower bound, this lower bound, this is a bit of improvement on some simple mechanism. There is always one user that gets best of n channels, and then the second one gets best of n minus 1, etc. So this is a simple lower bound. Actually, this can be generalized to a sequence of lower bounds that converges to the optimum. And this is the stable. So we can see that we always get at least 97% of the optimal utility. So this is pretty good. So with n square many iterations or many transmissions, we might get to 97%. That's not bad at all over the random ready phasing channels. Still, this is not, the n square can be quite large and channel changes, and we don't want to do that. So the next idea is to use what we call the opportunistic carrier sensing, an idea from Qin Zhao and Lang Tong. So they said whenever we want to give the channel to somebody, that has better quality, and they did it in order to minimize transmission energy in sensor networks, we can define a backoff period that is inversely proportional to the quality, and then the best guy gets a shorter backoff, and then he gets the channel, assuming that everybody can hear. So no hidden nodes. It can be generalized to RTS CTS schemes, but so So actually here we can do the same, but we can do a multi-channel version of it, multi-channel carrier sensing. So each user chooses on each channel a backoff that is inversely proportional to the quality of the channel. Well, it doesn't have to be 1 over the rate. It can be anything monotonically decreasing. Actually, we would like to do it differently in order to separate the timings. Otherwise, the high rates tends to concentrate near 0. So we need a monotonically decreasing function of the rate, and then each user determines the backoff period according to this, and then by the end of the contention period, let's see what happens. So this is an example. So these are the channels, these are the users. So channel 2, the quality of user 1 is 50, of user 2 is 100, and of user 3 is 10. This is the largest element in the matrix. So user 2 on channel 2 has a backoff that is like 0.01. So when 0.01 times pass, actually user 2 transmits here a busy tone and gets the channel. Then the others hear this, so they can still monitor the other channels for the rest of the contention period. And then we have this submatrix 16, 25, 12, and 20. So user 1 actually after 0.04, user 1 gets channel 3, so that one. And then user 3 gets the other channel. So by the end of the contention period, we actually found a stable matching. So that's really...
Well, that's why you
that's order 1, yeah, every packet we can do that. No, I have n channels, that's true, but I can monitor them parallel, right? So this is like parallel time of 1. Yeah, I agree that this is a bit cheating, but you cannot expect this. So maybe it requires a bit of extended contention period, but actually every packet you can do that. No, that's fine. So, so this is in a single packet, right? Okay, so that's and each packet. At each packet we convert to the stable matching, so whenever channel changes, we can actually change the allocation, and basically we replace gain-Shapley algorithm by carrier sensing. So that's a way to use carrier sensing to compute stable nets. So there are several practical problems. It requires fast channel switching at the transmitter. It requires infinitely many levels of channel quality. So this can be done using collision resolution and maybe spreading it a bit more. The paper includes several other analysis of these solutions. I don't think they are that interesting. It's more interesting is how to use the carrier sensing to solve the optimal matching. That's much more challenging. This is a linear programming problem. So what is the optimal matching? What is the optimal matching? The optimal matching basically can be phrased as a linear programming problem and solved by the Hungarian method. Hungarian method because Kuhn used 2 lemmas, each one was proved by a different Hungarian mathematician, so he called it the Hungarian method. But it basically was the first primal dual solution of a linear programming problem in 1954. So this was the first problem that was solved by primal dual, and the Hungarian method is just a special case of the primal dual. Only problem is that primal dual method is really non-parallel, non-distributed, nothing. So this is, but it is interesting to see how we solve this problem. So initially, if we write the problem, it's not clear that this is linear programming because we want to maximize some uij xij, such that at most one xij is 1 for each user. At most, at each frequency is allocated to at most 1 user. But xij should be either 0 or 1. So this is integer linear programming. Everybody knows integer linear programming is NP-hard. No way where we have good methods to solve it with large number of variables. But Kuhn actually said, okay, let's do what everybody is nowadays doing. Let's do relaxation. So we can relax the problem and hope for the best. And actually here the best happens. So we replace x between 0 and x is either 0 or 1 by the nicer constraint x is strictly between 0 and 1. So the problem turns into linear programming. It turns out that that this problem is actually simple to solve. And so we had 2 observations. First, the solution of the relaxed problem is always at least as good as the integer problem because we relax the problem. We have larger set of available feasible variables. And then if the solution to the relaxed problem somehow mysteriously ends up to be integer, then this actually solves the original problem. But this problem is known as what is called totally unimodular linear programming problem. which basically, if we look at the constraint matrix, every submatrix has a determinant plus minus 1 or 0, so the solution must be integer. So by solving this, actually Kuhn managed to prove that solving the linear programming actually needs this, and the primal dual technique actually converges in n to the third. So it involves some maintenance of the Lagrange multipliers, the duals, and the primal variables. Quite nice, but we will not get into it because we cannot parallel it, to make it parallel. So when we looked at it, I have a student, a very good student, Oshina Parstek, is now within 1 year is going to finish. So he saw the stable matching. He said, well, we must try to solve the optimal. So the first thing to do is there's the auction algorithm of Pertzacast. That's a really distributed solution to the assignment. So we can look at that one, and the algorithm is based on an auction process where the prices are basically Lagrange multipliers. And this is a parallel algorithm. Unfortunately, we will see later it cannot be done purely distributedly because there is a need for an auctioneer, and there is a need that everybody knows the prices. So, we don't want to transmit anything beyond busy tones. So we will have to change it, but I will give some overview of this because I don't think everybody knows this algorithm. So Pj is the price of object J, and this is basically the maximum of all the prices that were proposed by the user. So it's maximum over I of Pij. The reward of object J for person I is Aij, or actually it should have been Uij, but I merged two presentations, so it's inconsistent. Sorry for that. So the profit from object J for person I is basically Aij minus Pj when we have a price Pj. So this is the profit. So everybody wants to maximize his profit. This is the intuition, that's why it's an auction. And each person, and then there is what we call an equilibrium. So if each person is assigned an object Ji and Aiji minus Pji, the price that he's willing to pay is basically the maximum profit over all the objects. If this is the case for everybody, the system is in equilibrium. Nobody wants to bid for another object because he got his highest profit given the set of prices. The interesting theorem says that an equilibrium assignment solves the assignment problem. This is not so trivial. It's like 8 slides that I'm not going to show here because of time limitations. And basically, the set of prices solves an associated dual problem. We will not get into this. So basically, we have a naive auction algorithm. This is not yet the auction algorithm. There is a slight twist here. So the naive auction algorithm proceeds as follows. Each user looks at his initially they start with prices 0. Each user looks at his profit, which is basically the utility of the channel with the maximum utility, and then he wants to offer a price. What would be the price that he will be willing to pay? It's basically the difference between the profit on the best channel and the second best channel. As long as he's proposing this is still his best profitable channel. So you would increase it by the difference between the most profitable and the second most profitable channel. And then each one is doing this, and then the process continues. Hopefully it converges. So this is the process. So we have a bidding phase. Each user finds an object which maximizes the profit and then computes a bid. And the bid is basically, he is willing to increase Pj by the difference between the profit of the best channel and the second best. So these are the Mi and the Omega I. And so this is the bidding, and then the assignment is the user with the highest bid gets the channel. So this is simple. And the price are raised, and hopefully we get an equilibrium and everything is fine. The only problem is that if you, one of the users, for example, has the same profit on channel I and channel J, or channel J1 and J2, then he will not increase the price. So everything gets stuck. So we need to do something. And the idea is that basically we need to ask every user to pay for any bid, for every bid, a small amount of epsilon. This is enough to resolve this this convergence to the same profit. So we choose a non-negative scalar epsilon greater than 0, And then the price, we say that we have epsilon complementarity slackness. This is the definition of Bertsekas. If AIJI minus PJI is greater than is the highest profit up to an epsilon. An epsilon can be arbitrarily small. So we can think about it like every time that you bid, you have to pay an epsilon. So if you are within epsilon from the best allocation, you will not increase the bid. You will stabilize. On the other hand, if you have the two channels, then you will increase the other channel. Even if they are the same, you will increase the process. So now the price is increased by mi minus omega I plus epsilon each time. So basically it's inflation. Every iteration, all the prices go up, at least by epsilon. So this is like inflation, and then with this choice, the epsilon CS condition is satisfied, implies that we are almost optimal. So the theorem says the theorem of Bertsekas says, given a feasible assignment and a set of prices, we satisfy epsilon complementarity slackness. The assignment is within n epsilon of the maximizing total reward, and is optimal if epsilon is 0. So basically, by doing this, we can get an n epsilon optimal. But if the rewards are integers, and epsilon is less than 1 over n, obviously we get the optimal one. So actually, that's not too bad. We just pay by reducing the epsilon. If they are not integer, then there might be some strange phenomenon. You can always quantize them. So that's reasonable. And then the theorem says that this feasible assignment when the algorithm terminates is actually epsilon n from being optimal because it is epsilon equilibrium. So how does it work? Let's look at the matrix. So we have here, these are the bidders, these are the objects or users and channels, and then this user wants actually object number 2, and this one prefers object number 3, etc. So, and we assume epsilon is 3, just that it will be easy to compute everything. So 3 goes to 0. So we are looking at this limit. So now the price, the price that the first bidder will propose for channel 2 is basically 65 minus 51, which is 14 plus 3. This is the epsilon. We have to increase the price by epsilon, so this is 17. Similarly, user 2 will propose 8 on channel 2, user 3 will propose 20 on channel 3, and user 4 will propose 7 on channel 3, and he loses. So then, what happens is the next step, prices are updated, and this is the auctioneer. That's, everybody needs to know the price in order to update the matrix. And this is where you need a shared memory. And we don't want this. So this we will have to solve at the next stage. So basically we update each column by the price that was that won the bid. So the price was 17, 8, and 20, so we need to reduce the profit. Each user reduces his profit by the price that was agreed upon. Now, okay, so now user 4 didn't get a channel, so he actually increases the bid to 9 here, and actually gets that channel because the previous bid was 8. So now he gets the channel, and he increases the price by 9, and then he bids 17 because it's 9 is the increase over the 8 that was before. So now the price is 17, and now he wins. And then at the next stage, user 2 actually bids for user 2 bids for that, and we end up with this and total profit is 324. This is actually the optimal in this case. So we were lucky. Even though epsilon was 3, we ended up with the optimal solution. Okay, and
so if epsilon had been a different number, what would have happened?
The dynamics would be different.
Right.
But we will be always within 12 from the optimal. That's what 12, yeah, 4 times 3.
I see.
Okay, if epsilon was half, then we will be within 2 from the
I see. Okay.
But it might take longer. I'll show you later some simulation. One thing to note is that actually the total profit is not monotonically increasing by this process. So it's not that it's like a gradient method or anything like that.
By making the epsilon bigger, you more pressure these guys on.
Yeah,
Right,
converge.
right,
Yeah, so
right,
if epsilon
right.
goes to infinity, basically we get the stable matching. Okay, so epsilon goes to infinity actually gives us the stable allocation. So we can analyze the performance. Bertzikas actually did it. So it's n squared maximum of aij over epsilon. This is the number of steps, and then we can put quantization of these, and so this is approximately something between n to the third and n to the fourth in order to get the optimal. The only problem is that, so we can do epsilon scaling, which means that we, like in LMS, we actually reduce epsilon along the process. This actually accelerates the process. It's very hard to analyze. I haven't seen any analysis of this. But you can do epsilon scaling, so epsilon goes down. And then each user must know what was the other user's bid. This requires an auctioneer or some distribution of prices. This is something we don't know. So the question is, the question is, what do we do? So the bad news is that users do not know the bids. The good news is that we can modify this auction algorithm to get something that actually doesn't require to know the bids. Everybody bids against its own prices. And eventually, somehow, the whole thing converges. So this is like a magic, wishful thinking. So actually, it converges in finite time, and it has the same optimality bound like the original auction. So that's what I'm going to show you next. So we replace, and this was an idea for Shri, we replace the epsilon complementarity slackness by a local one. Local epsilon complementarity means that for each user, Aiji minus Piji, which is his own price, is greater or equal than the maximum of the profit over other channels by at most epsilon. So basically, each user actually is happy compared to the prices that he knows. It turns out, and it's not hard to prove, that at the optimal, at the equilibrium, if this is satisfied, also the epsilon complementarity slackness holds. So it means that if we manage to converge here, we actually converge to, we actually get an optimal solution. So that requires some proofs. I'm going to omit it here. It's not interesting. These are just epsilon, too many indices. Okay, sorry. So given okay, not controlling it very well. So given a physical assignment and the set of prices which satisfies L epsilon local epsilon complementarity slackness, actually the epsilon complementarity slackness condition is also satisfied. So this is the first theorem. It's not hard, and it's very lucky that we got it. Otherwise, nothing would work. And this actually ensures that when we converge, actually we get the optimal one, and we can show that we actually converge. So the same analysis of Bertzikas carries on to this. The interesting thing here, and I've already mentioned it, that in order to know whether you should stop to compute this complementarity slackness, actually this is local. You only need to know your own prices. You don't need the global prices. So there's no need to know the global prices, but we need to be able to replace the auctioneer. And that's what the carrier sensing, the opportunistic carrier sensing, will do for us in the next step. So I'll just show how it goes. So it begins actually the same way. So here we begin the same actually, because these are the first prices that each one is going to propose. The prices were 0. This is the same like the previous one. But now things change. This guy, the fourth guy, lost. He proposed 7. So now he can only update the prices based on what he knows, the prices that he knows, 0, 0, 7, and 0. So he will update the price on that channel. He will propose 6 on that channel, because this is now the best channel. The price was 0. 82 minus 79 is 3, plus the epsilon is 3. So he proposes 6 on this channel, and he obviously loses. But now he updates his price again, so he reduced this by 6. So basically, he's competing against himself until at some point he manages to get a channel, and then somebody else competes against himself. So that's the idea. So we slowly increase the prices until we manage to get the channel that we want, or one of the channels. So the dynamics is a bit different. It's a bit slower, but hopefully, not hopefully, it converges.
And they are resolved again using the same carrier sensing.
So this can be resolved using carrier sensing. I'll show in a minute.
Okay.
So So now he increases the price. So now his matrix is 76 feet, 79 feet. So he increases the price here to 13 and he actually wins this channel. And now, again, user 2 looks at his profit. He didn't update the profit because he was not kicked out from the channel. So now he sees that he has a gain of 3. He can increase the price of this channel by 3, so he proposes 6. And actually gets the channel because nobody wanted it. So the whole process converges. It turns out that the total profit or the value of this assignment is also 324 and it's optimal. So in this case, all the methods are optimal, but this is the coincidence. Or not coincidence, like people should want to get the numbers right. So if we compare the average percentage of the total reward as a function of epsilon, this is the auction algorithm, this is the modified one. So actually we are better for small epsilons because our price increases are less ambitious. So we lose a bit less, but it costs us more time. So all of them are within a certain percentage from the optimum. Remember that in this case, the stable was like 94% of the optimal. We can get here to 99 by choosing an epsilon that is small enough. We pay a fixed price in terms of complexity compared to the auction. So what is really interesting is to get the average time analysis of the auction and some simplifications, because worst case is n to the third. So the first thing to do is to reduce the complexity. We don't want n to the third, because even though this is purely distributed. Why is it distributed? Because now the difference, mi minus omega I, depends on the local prices. So each user updates his carrier sensing backoff based on his own prices. Inversely proportional. Eventually, he will win a channel. So eventually, the guy with the higher price wins the channel. So it doesn't matter. So the prices keep increasing until everybody gets a channel assigned. There is a small lemma that says that when all channels are assigned, because basically the process must stop, because it means that everybody is optimal. So this is part of the analysis of the convergence.
How do you assign the initial prices?
Price is 0. We start with 0. Yeah, there is a problem with inflation. So if we have an ongoing system, so we converge and then channel changed, now the prices are higher, so prices always goes up, like in real life. So we actually, at some point, we need to rescale the prices. So there is some issue with that if we really want to have a system implementing it, but we are not at that stage yet.
Do you rescale the prices or you just subtract?
Subtract, yeah. I mean, okay, not scale. Actually, I need to subtract, but I don't know how much to subtract because, basically scaling is easier. But, okay. There are some subtle things here that we haven't worked out completely for an adaptive system. This is an interesting research problem. Okay. So, this is totally distributed. Everybody gets to the channel based on opportunity carrier sensing or multi-channel opportunity carrier sensing. It guarantees a solution that is epsilon n from the optimal, but the convergence is slow. So what can we do? So the first approach is very uses actually random graph theory. So we say basically we want to chop the worst channel. We hope that we get the best assignment where everybody gets like something like alpha log n of get assigned something which is like alpha log n of one of the alpha log n best channels. So that's the first approach. So what we say, sorry, this is just worst case complexity is similar. I'll skip that one. So we might want to modify the algorithm, and they say each user actually puts the correct rates on alpha log 2n, and he puts to 0 all the other channels. So everybody will not settle for something that is not one of his best alpha log n. Note that by order statistics of IID random variables, this is actually very close to the optimal, because the alpha log n order statistics out of n is really, it's intermediate order statistics, it's really close to the optimal. So if we manage to find any allocation, not even the optimal, using the best alpha log n, we are asymptotically optimal already by theory of order statistics. So this is pretty easy. The only thing is to show that there is at least one matching that achieves this, and this basically, we can think about it as a random bipartite graph. And this random bipartite graph becomes connected with probability 1 or has a matching with probability 1 as long as alpha is greater than 1. So if we took the best log n channel, we will not get anything. But if we take 1 plus epsilon, it's fine. And then the probability of success, actually, if we do the analysis of the random graphs, is 1 minus 1 over n to the alpha minus 1. So alpha equal 2 gives us 1 over n. We can take larger alpha, and then convergence is a bit slower. So this does the work in alpha n squared log 2n times. So we already gain a factor of log n over n. Can we do better? So basically noting that the best alpha log n is good, and any assignment that takes one of the best alpha log n channels is good, and allows us to remove this, because what would be sufficient is to take any matching where each user gets one of his best alpha log n channels. That would be sufficient. And we have one by the Amir theorem for bipartite graph. So basically, instead of putting the rate there, we just put 0 and 1. So we get again an auction algorithm, but now prices are either 0 or 1. It turns out that we can replace searching for this matching naively is n squared log n, but actually recently we have an algorithm that does it in n log n many steps, and this is actually the best that you can do for a random matching. And actually there are quite nice theorems involved in proving all these facts, like we use some lemma of Aldous. There is a very nice theorem about random assignments. If you take random assignments where the values in the matrix are uniformly distributed between 0 and 1, the worst assignment has expected value of pi squared over 6. This was open for many years. It was proved by Aldous in 2001. So this doesn't help us, but one of the lemmas actually is very useful and does the work for analyzing the convergence. And then some other work by Notani enabled us to analyze the auction, which turns out to be equivalent to something called Cauchy label algorithm for matching. So we find any matching where each user gets one of his best 2 log n channels with high probability, we get a matching. If we don't get a matching, then this happens with small probability, then we run the optimal one. If we end up without getting a matching, we know that, so we run the optimal algorithm that rarely happens, so it doesn't affect the average time. It still gets us a good matching, and we know by all the statistics that this is actually a good matching. So complexity can be actually reduced, and this is so we have a bound on the outage probability. This is the 1 over n, for example, and this is the actual outage. It's much smaller than 1 over n for a small number of users. Typically, we would find a matching which is where every user gets one of his best 2 log n channels, much better than 1 over n that the theorem predicts. It's an upper bound. So you can see that here it's very tight, but actually for the small number of users, this is not bad. Like we get with probably 0.01, even with 10 users, there's only 1% chance that we will fail. So this is actually.
What do you mean that small number of users want to have n channels and n users?
Yeah, but we asked how does it scale with the number of users. So the
okay,
asymptotic was in the number of channels and
Number
users.
of channels.
Yeah, so for already 400, our bound is actually quite tight. They say the Shremim, because this is really a threshold phenomenon. But for small n, actually this becomes straight, so it's actually better than what the theory predicts for small number, and this is actually important. Okay, and then it seems that the perfect matching is not that good. It gets to 95, around 80 users. The truncated auction, where we just put zeros and find the optimal, actually, with very high probability, actually finds the optimal one. Actually, if it fails to find, we just get a random reward, but this happens with small probability, so it doesn't affect the expected reward, basically, so we get very close to 1. Okay, that's... So basically what I showed is that communication protocol can assist in distributed computation in a way that is different than what people are typically doing. And multi-access channels can do much more than simple addition. We can actually solve linear programming problems using carrier sensing, which is an unexpected. So this is basically communication for signal processing. Usually we talk about signal processing for communication. This is a work on communication for signal processing. So there are some extensions. We can solve cooperative game theoretic problems. I did it with Efi Zahavi, and recently we managed to prove it actually always converges using some, Efi did some interesting analysis of the atom of functions for these problems. So this is really new, and then this can be used also for distributed detection and estimation. I work with my student at former student Kobe Cohen. We did some work several years ago on distributed detection for sensor networks. So actually we can also do this for energy limited estimation. There are some nice generalizations and others, but I think I'll stop here.
I had a small question. I think I've already covered that, but I just wanted to clarify. When you are talking about the probability of the optimal algorithms being equal to the, let's say, more complicated algorithms, what is the distribution you are talking about?
So
the Rayleigh model?
Well, this is actually holds in much more general as long as we have a thin tail distribution. So as long as the tail is not heavy, for example, if we have like bounded utilities, that always works. And actually, this is the case of interest because the rate on a channel, actually Yair knows it very well. We have a really fading channel, but it will never amplify by 20 dB, right? So basically, we should look at truncated ones. There's a story that Yair came to me with a proof and said I used the Lebesgue dominated convergent theorem. And I told him, you don't need that. But it turned out that because the Rayleigh channel has a small probability of amplifying infinitely much, he actually needed that. So sometimes
the model
punishes you and requires more. You think that the model is simpler, but actually if you truncate, sometimes it's better. Also with heavy tail distribution, it's many times the case. So, yes, what was I saying?
So they found it.
So for any bounded, for any thin tail, as long as basically the order statistic is what is called intermediate order statistics. So it's close to the upper bound, but not really. I mean, it's not a constant within like the best 5 channels, but best log n is what is called an intermediate. It goes to 0. The log n over n goes to 0. So that's kind of intermediate order statistics. That's good enough to show us asymptotic optimality.
I have a question. So if it was a MIMO channel, what where you have multiple streams per channel, what would be the right number there?
The right.
Because right now it's just an SNR pretty much, right?
Yeah, it's SNR. So
what if there's multiple?
Well, I can do the dirty trick and assume, okay, I do orthogonalization, zero forcing and scheduling, like you know very well.
Yeah.
So I schedule the users, and then probably it will be the order statistics of the log 1 plus SNR and the eigenvalues. And I want to allocate also in the multi-user MIMO. Well,
No, I was just talking.
I mean, this would be interesting to analyze.
Yeah, but the utility could be the capacity of that stuff.
So utility is the capacity.
The capacity.
Yeah.
So if it's MIMO, you wouldn't use the MIMO capacity.
For each special sub-channel. Yeah. So but there will be problems because when I do like zero forcing beamforming, there are some. It might be that it's better for me to choose the second channel here and the third there. So analysis might be.
Well, that's what I'm saying. Yeah, it becomes interesting when there's
Yeah, definitely
multiple,
interesting is a good word.
I was just wondering if you thought at all because I'm not sure what the right metric is then. In that, it's okay. I mean,
Well, this is like what is the right metric for choosing the quantum constellation in a MIMO setting?
Yeah.
It's similar. I mean, you don't have like a decent SNR measure, right? Because you have different.
If you can only choose one.
If you can only choose one, if you do the ICM over a MIMO, you get similar issues, and these things become a bit realistic. Okay, thank you.
Great, thanks.